I owe you one. I owe you an A. You get an A for the semester. Sound good? You don't even need to show up anymore. All right. So today's lesson is all about what's called improper integrals. And what an improper integral is, there's one of two types. Number one, it's if one of your limits of your integral is an infinity sign, meaning you're integrating out to x being infinity forever. The other type of improper integral is if you're trying to integrate across a vertical asymptote. Now, the first one, when one of your limits is infinity, is easier to see because there's nothing sneaky in there. There's nothing being hidden. They're showing you have infinity here, deal with it, and that's what I'm going to teach you today. The vertical asymptote ones are a little bit more sneaky because I'm going to show you an example here of what we're going to do. If you look at example 4 right here, that function has a vertical asymptote at 0. And one of your limits is 0. What you're going to find out is if you didn't recognize that this had a vertical asymptote and you just tried to integrate it using your normal power rules, using the fundamental theorem of calculus, you would get an answer. What you're going to find out is this integral actually does what we call it diverges. There is no answer. So if you don't recognize that you're either integrating across a vertical asymptote or one of your limits is a vertical asymptote, you get the wrong answer on these ones. And that's why I'm not a fan, because they are sneaky. You have to be on the lookout for it. But anyway, so the first types we're going to deal with is what happens if one of your limits is positive infinity or negative infinity. In this section, we're going to be dealing with limits again. Limit properties show up because infinity is not a number. Now we can approach infinity, and anytime we're dealing with approaching something, that's when limits get involved. And so that's what's going to happen. You can notice in this gray box here, there's a lot of limits going on. So we're going to be dealing with limits and their properties. And what's going to happen is if you look at this gray box right here, if one of your limits of your integral happens to be infinity or negative infinity, that introduces a limit. Notice how we write this notationally. We don't put the infinity here, but we actually replace it with a letter, either A or B, depending on our lower or upper limit. And we take the limit as that letter approaches infinity. And so that's how you deal with the infinity being either the lower limit or the upper limit. You introduce a limit and have that letter approach the infinity instead. And then we pretty much tackle the problem the same as all the others. We just have to deal with limit properties, as you'll see. When we're dealing with improper integrals, 2 new words get introduced, which have a huge role as far as the rest of the semester goes. And those 2 words are converge and diverge. These 2 words become super important throughout the rest of the semester. What it means to converge is basically if the limit exists, we're saying that integral is actually approaching a value that we can consider to be the final answer, the actual answer. What it means to diverge is it means the number's either too big to count or it doesn't approach something quickly enough by mathematician standards. And so we say the integral diverges. What we are headed for in this semester, and I think I've alluded to this, but we're basically going to have a series. You don't need to write this. But the biggest thing in Calc 2 that you guys will see if you end up redoing Calc 2 in college is you're going to have stuff like this. You're going to have a series like this. And you are going to be adding up infinitely many things. And the question we are going to end up getting, it's not today, but the question is going to say, hey guys, does this series converge or diverge? And you're going to have all these different tests and all these different ways of determining if an infinite series converges or diverges. We'll learn all those. It's quite boring. I find this semester of Calc 2 to be quite boring once we get to that stuff. Again, I probably shouldn't say that, but I don't know. It's just, I remember doing it in college and just being bored out of my mind. Because it's like, once you look at this one, you're like, oh, that one diverges. Then the next one comes along. You're like, oh, that one converges. And then the next one comes along. You're like, that one converges. That one diverges. It's just boring. what it leads to is kind of neat. Like it's what it leads to when we get into, I don't know how much words you guys know in math. I don't know if you guys have ever heard of Taylor-Maclaurin polynomials or Taylor-Maclaurin series. You guys ever heard of those things, those words? Okay, that's what it leads to. Basically what it leads to is us figuring out, how does the calculator know what e squared is? Like when you type that into your calculator, how is it programmed to know what that number is? Or how does your calculator know what sine of 5 is? That's what that stuff leads into. It's kind of programming and things like that. So the lead up is kind of boring. Where it heads is kind of interesting. Anyway, all right. So we're going to do this very first one. It says evaluate 1 over x dx from 1 to infinity. And I want you to understand what this means graphically, what it's asking you to do. Okay. Imagine I graph the function 1 over x from 1 to infinity. Well, the graph of 1 over x in the first quadrant looks something like this. This is just in the first quadrant. It's down here as well, but since we're just doing 1 to infinity, we're not worried about that part. So what this question is saying is, okay, let's say we integrate from 1, so that's our left boundary, all the way to infinity. So here's the deal. There's an infinite amount of stuff underneath that function. Like that function's never going to touch the x-axis, which means if we integrate out to infinity, there's always going to be stuff above the x-axis below that function. That doesn't just necessarily mean that we never can count how much area there is, as we'll find out, okay? But here's how we go ahead and tackle this problem. If one of our limits is infinity, we rewrite this instead as the limit. Now, this is just my preference. The letters you guys pick are not going to matter. But anytime I'm replacing the upper limit, I use B. And if I'm replacing the lower limit, I use A. Because we integrate from like A to B. So that's just how my brain works. So I'm going to have B approach infinity. And I'm going to integrate from 1 to B instead. Now, we deal with the integral stuff and we deal with the limit stuff towards the end. We have to carry it through the work notationally, but we're going to deal with the integral stuff first. So this is going to be the limit as b goes to infinity. And now I'm going to integrate 1 over x. And so that's going to be the natural log of absolute value of x. I don't need to put the absolute value sign because the numbers we're going to plug in, it's all positive. We're dealing from 1 to infinity. X is going to be positive in this case. And then I'm going to plug in b and plug in 1. So I'm going to have the natural log of b minus the natural log of 1. We know the natural log of 1 is 0. But now this is where the limit properties come into play. If b is approaching infinity, well, let me ask you guys this. What's the natural log of infinity? It's infinity. It's going to infinity. Okay. What that really means is this limit doesn't exist. This limit does not exist because it's going out to infinity. So what we say is this integral diverges. It's too big to count. That would be the answer to this question. That integral, that improper integral diverges because the limit doesn't exist. Now, the reason we have to use this limit notation is because mathematically, you can't plug infinity into places. Like this limit does not exist, but it would not be mathematically okay to like write the natural log of infinity. Like they would look at this and be like, that's not a thing you can do. You could take the limit as a number goes to infinity of the natural log of that thing, but you can't like put infinity in your math. That's why we have to use limits. Well, let's look at the next one. Next one's kind of fun. Same idea. If I graph this one, you don't have to graph these. I'm just trying to get you to see kind of what is going on. 1 over x squared is kind of that volcano function. So it looks like looks like this here. And so again, we are integrating from 1 to infinity. It looks like the same exact problem. Gosh, smack him. Wake up. It looks like the same exact problem, same exact graph, right? But let's look at what happens on this one. So again, I'm going to take the limit as b goes to infinity. And I'm going to integrate from 1 to b. Instead of writing 1 over x squared, I'm going to write x to the negative second, because we can actually use the power rule on this one. The last one we couldn't, but this one we can. So now I'm going to integrate x to the negative second. So I bump that up to -1, divide by -1. So -1 over x. Did I do that right? And then I'm going to plug in b, and then I'm going to plug in 1. And I'll wait a second. So I plugged in b, and then I'm subtracting -1. So I just put the +1 there. Now this one's more interesting because if I take the limit as b goes to infinity, well, imagine that b value getting really, really big. This fraction turns out to be 0. Like 1 over infinity is 0, and then 0 plus 1 is 1. We actually get an answer to this one. So this integral is 1. It converges to 1, we say. So it's quite interesting that it's almost the same graph, but this one is getting close enough to the x-axis quick enough that we can say that area is converging to an actual number, whereas the previous one we couldn't. The functions, when I talk about series, like I was mentioning over here, the functions 1 over x and 1 over x squared kind of become two really, really big tests that we'll be getting to. 1 over x diverges, but 1 over x squared converges, as we'll find out. Fun stuff? Yeah.
For our answer, do we just write converges to 1 or 1 or?
Well, the way I would write it, you know, if they say evaluate this, I would say this equals 1. You wouldn't even need to write converges. Vincent. Hi, Vincent. Did you get the boot? Still joining? He'll figure it out. The next one, so, okay, a couple years ago, I was making these notes, and the next one, I was like, ooh, this one looks fun. It's not one, I'm just going to show the answer here in a second. It's not fun, but that's besides the point. Anyway, the reason I picked this one is sometimes your lower limit and upper limit are negative infinity and infinity. When that's the case, we need to pick any number in between negative infinity and infinity and split this up into two separate integrals. Like I'm going to pick 0. Oftentimes you're going to use 0. 0 is the nicest number to use. And so what I'm going to do is split this up, as you'll see here in a second. But the graph of this, I want to show you the graph of this. I don't know if you guys would know this or not. I would have no idea. The graph of this function, oh, crap. God dang it. Looks like this. I didn't mean to hit the x-axis. The graph looks like this. And so I'm really trying to find the area of all this stuff here and here. And I'm going to split this up as 0. And so here's what the first part of this is going to look like. All right, I'm going to split this up into two separate integrals. I'm going to integrate from negative infinity to 0. And then add the integral from 0 to infinity. I'm going to talk a little bit more about this problem, and then I'm going to put the answer up. But again, conceptually, the reason why I picked this problem is if both limits are infinity, you can pick any number. You can pick 1 or 2. It doesn't matter. But you need to pick any number to split it up, because now I can just write this as 2 separate limit problems. Like I can tackle the left integral and have a go to negative infinity, and then for the right one, have b go to infinity, and do 2 different problems. So let's focus on the left one. Let's say I want to find out this integral right here. Well, so the way I'm going to write this is the limit as a goes to negative infinity, and then the integral from a to 0 of 1 over 1 plus x squared. And now I would need to integrate 1 over 1 plus x squared. What is it? It's arctangent. This is the one that you would just need to know. U substitution is not going to work because there's no x on top. Decomposition is not going to work because the bottom is not factorable. This is just the one you have to know, arctangent. It might show up. I would doubt it, but it might. So I'm going to have the limit as a goes to negative infinity of arctangent from a to 0. This is where I put it on there and I was like, oh, this is going to be fun for them. And I was like, hey. So now I got to plug in 0 and plug in a. So it's going to be arctan of 0 minus arctan of a. And then this is the part where I highly doubt you guys are going to have to know your inverse trig values. I don't see it happening. Anybody know arctan of 0? If you had to guess. Nope. 0. What about arctan of negative infinity? No. No. I think it's negative pi over 2. This is where the fun ran. Like, it wasn't fun anymore. So I actually didn't even know. When I made these notes up, this was 2 years ago. The first time I taught this course, I made up all these note outlines, and then I made the keys like a day or 2 before I taught the lesson. And I got to this part, and I didn't know this. I was like, I have no idea how to figure out what arctan of 0 and arctan of negative infinity is. So you know who I went to? No. Who's the trig guru around here? Mr. Porter. Trig is his jam, man. So I walked over and I was like, how do I know that arctan of negative infinity is negative pi over 2? And here's what he showed me. I thought it was really neat. Again, I don't think it's something you have to know, but here's why. He said, well, draw the graph of tangent. So that's the graph of tangent. You guys remember from your posters, your projects that you guys did? So that's the graph of tangent. And when you're asked about arctangent, now that's the y value and you're looking for x. Like that's what inverse functions do. So if I am asked to find arctangent of negative infinity, this is saying as the y value goes all the way down to negative infinity, what x value are you getting close to? So as this graph goes all the way down to negative infinity, the x value is getting to negative pi over 2. So I would have no idea. I wouldn't have any idea. And I don't foresee that being a thing you guys have to know. So I'm going to put up the rest of this answer. But the main I didn't want to just take it off the notes. I debated on that. I was like, well, I could just take the notes off. But I kept this on mainly for you guys to realize and see if your limits are both infinity, you have to split it up at any number. So here's the answer. It actually does converge. It converges to pi, believe it or not. So I'll put this up. Are we having fun yet? I will say these problems look challenging, confusing. The only ones I've ever seen show up on the AP test are pretty like basic forms of them. They just want to see if you know how to deal with an improper integral. They're not trying to like bust you. And that's kind of the nice thing about BC. In the BC test, one thing that when I went to that conference, they said since there's so much to assess, it's like you get the basics of everything to see if you know it. Where on the AB test, it's like, okay, now we have more to play around with. They can ask even more challenging questions. So the BC test is kind of nice in that way. They know there's so much. They want to see, do you know the surface of it? I don't know. The other one, which, like I said, it's the same type of thing. It's just a little trickier because you have to recognize it, is when either one of your limits is a vertical asymptote, or if you're trying to integrate across a vertical asymptote. You need to be aware, be on the lookout, and be careful about that. We treat it very similarly. So I'm going to just jump into example 4 and kind of show you. So this one here, we're integrating 1 over x cubed from 0 to 2. So graphically, let's kind of think about what this is asking us to do. The graph of 1 over x cubed looks like the graph of 1 over x. It's like the same graph, but probably gets closer to the axes quicker. Looks like this. And so we're integrating from 0 out to 2. Let's say 2 is there, which means now we're finding all of this area and stopping at 2. So we still have technically like an infinite amount of area. We're going to be dealing with limits. If the limit exists, then that's going to be our answer. If the limit of whatever we get doesn't exist, then we say the integral diverges. That's kind of where our head needs to be at this point in time. Well, we can't really have 0 be our limit. We can only approach 0 from the right side. So when we're dealing with vertical asymptotes, one-sided limits come into play. We can only integrate to that vertical asymptote, in this case, from the right. So here's how we write this. I'm going to take the limit, and I'm going to have that lower limit be a. So a can approach 0, but it can only approach it from the right side. There's nothing going on the left side. And then 2 is still the upper limit. I should have just wrote x to the negative third. The setup of these problems is really the hardest thing, because once you set up the limit notation correctly and all that stuff, now you just do what you guys know how to do. We're just going to integrate like normal. So the limit as a approaches 0 from the right, we're going to integrate x to the negative third. So negative 2 divide by negative 2. So negative 1 over x squared, negative 1 over 2x squared. And then I'm going to plug in 2. And then I'm going to plug in a. So plug in 2, negative 1/8 minus negative, so plus 1 over 2a squared. Now again, this goes back to kind of limit properties, but so this is negative 1/8. But for this one here, imagine taking a limit and plugging 0 in for a down here. I would get 1 over 0. I can't have 1 over 0. That's undefined. What that means is, since that limit doesn't exist, which it doesn't, then this integral diverges. So this does not exist, which means the integral diverges. And then the next one. So the next one is similar, but as I mentioned, if we don't recognize that this function has a vertical asymptote at 0, and 0 is inside -1 to 2, like if we don't recognize it or see that there is a vertical asymptote within the interval, and I just forget that, and I just try to integrate this problem like normal, I'm screwed. Because it's going to turn out this integral diverges. I'm spoiling it. Sorry. This integral diverges. But imagine you didn't recognize that, and I just integrated x to the -3rd. I plugged in 2. I plugged in -1. I got my answer. I don't know what the answer is, but I would get an answer. I'd get a number. I'd be wrong. So it's just something we have to be on the lookout for. The nice thing is, if you're taking your test, like, and let's say question 2, it happens, odds are it's not going to happen again. They're not, I mean, they have so few questions to ask. They're not going to have more than one question be devoted to any one topic. I'll say that. All right. So 0 is kind of the issue. Here's what the graph looks like as I drew up above. And we're integrating from -1 to 2. Okay. So 0 is the issue here. We're going to split this up at 0, at that vertical asymptote. So the first thing I'm going to do is integrate from -1 to 0. Then I'm going to do from 0 to 2. But anytime you have that vertical asymptote, that's one-sided limits. That's where one-sided limits come into play. So if I'm doing from -1 to 0, I'm going to have the limit. And if the upper limit is 0, I'm going to use b. So b, the upper limit, can approach 0 from the left. Well, you guys see how I write that there? I'm having 0. Oh, no, b. Let's speed that up. So my upper limit is b. B is that vertical asymptote, and I can only approach that vertical asymptote from the left. Then for the second one, now I'm on the other side. So now I'm integrating from 0 to 1. Well, now I'm going to use a approaching 0 from the right. When you're dealing with improper integrals, this is kind of a nice thing. If you're adding two things together, if one of them diverges, then the whole thing diverges. So like on this first one, let's say that, I don't know what happens on the first one. It probably diverges. But let's say on the first one, we get an answer of like 2. And then we know the second one diverges. Then the whole thing just diverges. And going back to the previous one, we already figured out, like we already did this right here. We did this problem. So since this diverges, the whole thing diverges. It's interesting, but probably my least favorite just because of the notation. It takes me a second, like, to get the notation right and put the right numbers and letters and minus and plus signs. That's why it's my least favorite thing. Not that it's excruciatingly tough. You just got to take your time a little bit more. And I'm one where I do things a little quicker. So I don't like this, but that's just me. Questions on improper integrals? Okay. Then what you guys have for the remainder of this class, you guys have a 5-question quiz. You guys at home are going to have this too. And you guys in here, I'm going to pass it out. You'll have a hard copy. You guys can use your notes. All right. So any formulas you need, you guys can use your notes. You guys at home, you can use your notes. I'm going to give you guys 20 minutes on this. I don't think, especially having notes, I don't think it will take you guys 20 minutes. But I'm going to give you guys 20 minutes. So which means for you guys at home, right now it's 11:22. We'll say it's 11:25. So I would like you guys to submit this to Canvas by 11:45. It is on Canvas, and submit it to that quiz. I hope I'm saying that right. Non-calculator. Just make sure you show your work. Yes, that is that. So you guys at home, I don't mind if you like write it on paper. that's fine. If you just want to pull it up on Canvas and then just submit it to that assignment, I'm fine with that. Or open it in Notability, whatever word. I don't care how you guys turn it in. You guys have any questions? You guys are gonna be able to hop off. As long as you turn it in within 20 minutes, that's fine. Then you guys have an assignment. I don't know if I explained that well, but you guys can go if I did. Okay. All right. Stop the record.